Hey everybody, this is Larry. This is day 10th day of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on the Discord. And here's today's prompt: finding a multi-level doubly linked list. So in this prompt, you're supposed to be given a doubly linked list, and you're supposed to try to figure out a way to find it, right? And the way that I thought about it, in terms of just visualization, is that you're given this multi-linked list from example one, which is this is a mess to look at. This is slightly less of a mess, but the way that I think about it is that if you really look at it, it really just is a tree of it's just a tree, right? And what I mean by that is that if you look at this node 3, you could look at going down to 7 as going to left on a tree, and 3 going to 4 is going right on a tree, right? And once you recognize that, and looking at the example where you always want to go down and then keep on going down and then come back up and so forth, that's just like a regular traversal of a tree. And with that, you could use depth first search or just any tree traversal. The way that I did it was by using pre-order, because I look at 1, 2, 3. So that's kind of the theory part of it. But the implementation part is a little bit tricky. There's a lot of possible edge cases. Definitely stay tuned and watch how I solved it live when I first saw the problem. And this is the first time I've seen this problem, I think. But yeah. But the thing that in terms of implementation, I did recognize that it was a depth of search and a tree thing very early. But in terms of implementation, it's a little bit tricky, because for a doubly linked list, you have to, for example, this 12 has to connect to 9, right? So what I did was, and you have to connect the 8 with the 11, which is much easier, I think. But yeah, so what I did was that for each depth first search, so this is my depth first search thing. This just kicks it off by, passing in the head and then getting the new head, which should be just the old head. But yeah, so this depth first search, my invariant, my contract for this depth first search is I return 2 nodes. One is the head of the sublist, and then the tail of the sublist of this recursion. And from that, well, the base case is if node is none, then just return none. It doesn't really matter. Otherwise, we keep track of the next and the child. We go to the child first, getting both the head and the tail, I call it last, of this subtree, if you will. Set the current nodes next to the new head, which is the child, or should be the child. That part should be true no matter what. And then we set it back where the child points back to the node. Got a little bit worried there, but yeah. And then after we process the left side of the subtree, which is what this is, we process the right side of the subtree, which is that again we depth first search of the node that points to the right side of the subtree. If you using our terminology, we get the next head, which should be just node next, and then we set the previous last, which is this is a little bit tricky, which could be a number of things, right? Or 2 things. Previous last could be either the last from our depth first search of the child, or if we have no child, we just use it to the current node itself. And then the next of that would be the next head, which is again node sub next. But yeah, we just keep the naming to keep it consistent. Technically speaking, actually, now that I look at it, I actually don't need to return the head of it, because that's implicit. But I just wanted to make sure that my understanding was clear. And when you watch me implementing this live, you'll note that, like, I could have gone a number of ways on different things, but I just wanted to make sure that I understand it as clearly as possible. And yeah, so this is the relationship of getting the last node, which, and then make it connect to the last head or the next head. So like this is like 12 is the last node from this branch from 8. So then now we return that to connect it to the next 9, right? So that's kind of the idea. And also again, we just, because it's a double linked list, we just point it back. Yeah. And the complexity of this, because it's, and we just set the child to none because we don't want it to go down. So yeah. And the complexity, the time complexity of this will be O of n for time, because we look at each node once, and we do constant number of operations. The space complexity will be O of h for the height of the tree, quote unquote, where it could be like, you know, however far you go. But of course, in the worst case, in a linked list or child list, it's going to be O of n, but all of it allocated on the stack space, or on the core stack, sorry. But yeah, yeah, that's all I have for the explanation part of the problem. Let me know what you think. Let me know if the visualization helped. I think once you're able to think about it as a tree, the problem becomes more, you know, more feasible. Because I was a little bit confused in the beginning as well. Yeah, stay tuned to watch me solve this live right about now. Hey everybody, this is Larry. This is the 10th day of the July Leetcode Daily Challenge. Let's get started on today's problem. This is the live coding portion. Hope you enjoyed the portion that came before this. Finding a multi-level doubly linked list. You're given a doubly linked list in which, in addition to the next and previous pointer, you could have a child pointer, which may or may not point to a separate doubly linked list. These child lists may have one or more children of their own, and so on, to produce a multi-level data structure as shown in the example below. Find the list so that all the nodes appear in a single level doubly linked list. You're given the head of the first level of the list. Okay. I have to see what flattening really means. Okay. So the head has this thing, and there's a child going from 3 to 7. What does flattening mean? Flattening means that, okay. Why 8 before 4? Just understanding the problem right now, but it seems like we just keep on doing that first search going children, and that'll be okay. Of course, we have to actually be careful to create the doubly linked list and stuff like this. But conceptually, the order is, I think I now understand the order. Oh, okay. Though the test case is going to be really annoying to write, but that's okay. Okay, so yeah, the number of nodes is only 1,000, so you could actually do worse, but I don't think we have to. We would just do a depth first search. Basically, in a weird way, you can think about a children is the left node, and then the next pointer is the right node of a tree, and then from that and then it's just a regular pre-order traversal, it seems like. And of course, again, you have to be careful to actually create a pointer in a good place, but conceptually that should be okay. Do we have to return, like, do we have to construct it on the way, or do we have to do it live? Let's try to do it live, and then we'll see. Why is this head? Okay. So yeah, let's do a depth first search node. So basically, we want, which order do we want? So let's just say we have this, we have some number that points down to C and go to B, right? So in this case, it'll go A, C, and then B. So it's actually pre-order, okay, because it does the A first. I just want to make sure in my head that I know well, I have an idea of how to go about it. So, okay. So I'll do this recursively. So that means that I want to return node at the end. And then I want to do node dot, if node dot child is not none, node dot next is equal to DFS node dot child. Oh, well, you have to do something smarter than that, but I'm just thinking it through, because what we need though after this is the last node on this list. So maybe I have to do something little bit. Okay. first of all, let's cache next node is equal to node.next, node child, just for symmetry reasons, though I think we, go do this immediately anyway. But what we want though is that, if node node next is not none, then we do, last dot next is equal to DFS node dot next, right? Something like that. And then here we want to, so I guess we actually want to return the last node. No, we want to return the first node and the last node, maybe something like that. Yeah, so here then, okay, let's focus a little bit. So we have head last is equal to this thing, and then we have node dot next is equal to head. Let's start by head is equal to itself. Just do none for now, and then last is also equal to well, just this node. It's okay if both of these are these node, but if node dot next is not none, then last dot next is equal to we want to get the next node, which is just node dot next. This we're sure about, and then we want to get I have to think about the states a little bit. H2AP for now. These are placeholders. I'll rename them. I'm trying to think through a little bit what that means. This gets the last node, so this is the new last node, but we want the previous last node. Okay, fine. Previous last equal to last, and then we just set this is equal to, and do we care about the next node? No, I guess it doesn't really matter what the next node is, because we already set it. No, that's not true. Okay. Next head. And we now look at the previous last. Next is equal to next head. Also, we have to reset some stuff, which is that once we finish this, no matter what, we always set node.child is none because we want to complete it, something like that. Anyway, and then now head, new head is equal, and we don't care about the tail, is equal to DFS of the head, and then we return new head, something like that. I don't think this is quite right, but I want to just give a nice look. It's not a wide double linked list. Oh, that's right. It's a doubly linked list. So that means they have to point some nodes back. And that means node.next is equal to head. So that means that node child dot previous is equal to node. And next head dot previous is equal to previous last. Something like that. Still not confident I'm right at all. There's a lot of pointer keeping track of pointers, so it's really hard to I don't know. For me, I feel like it's hard for me to keep track and make sure that I got all the cases right because there are a lot of interactions, right? So yeah, though I did happen to get this thing right. So let's try again. I don't know how. I guess I'll copy the other test cases. Because it's not super clear to me how to generate more test cases, to be honest. Let's at least see if this is right. Okay, so that looks good. I guess I could, I mean, I should really do an empty one. Yeah, okay, that makes sense. I don't have a base case. Or I guess this is okay actually. It's just that I don't keep track of one case because all the other ones are implicit nuns based on these two. So, okay. But, oh, yeah, right. Let's see. I want to do one where it's all child, but it's still not super clear to me how to generate test cases. How should you just vertically create them? Okay, well, I'm just going to submit it because usually I would, and I definitely would recommend for these kind of things, you actually need a lot of test cases to go over what your assumptions are. I'm a little bit lazy today, mostly because I know that they have test cases, but also because the serialization is weird. I think if there was a way I can, I guess maybe I could have just written something to something generator or something like that. But it's just a lot of effort. But definitely, if you are doing production code stuff, that's definitely what I would do. But yeah. Okay, let's go over the complexity and the space complexity. So this is actually a pretty straight depth first search, and given the way that we talked about it earlier, you can look at from 3 to left, it's just going left on a tree, and 3 to 4 is going to right on a tree. And if you do that, then this is literally a depth first search where all the time complexity will follow as well, which is that because each node is only visited once, it's going to be O of n, and space, well, we do keep stuff on the stack, so it's going to be the O of height of the tree, quote unquote, which is the height of the length of the height is the longest children, or basically similar to that, which in the worst case could be O of n. Yeah, I mean, I think this is actually a cute, interesting problem to kind of ask you in a perspective way. I think the only thing that makes it more annoying is that it's all the like you have to make sure you get the notes okay. I think, well, I mean, I think I got lucky a little bit on the first try because I don't know. To be honest, if I have to do it again, there might be a good chance that I miss one of these edge cases. So yeah. But conceptually, it's a problem that I dig because it is otherwise a really straightforward depth first search with the little fun, tricky thing. Yeah, that's all I have for this problem. Hit the like button, hit the subscribe button, join me on the Discord and ask me about problems. And I will see y'all tomorrow. Bye-bye.